But today, what I will be discussing with you is how to build a C++ extension. More specifically, we're going to be going over the specific use case covered this morning for a plugin in which we will be looking at cell spreading on an adhesive, a field with patterned adhesion spots, and then modifying the energy functional so that this contribution will saturate at large adhesive numbers. We will then look to make this controllable at the XML level as a good way to kind of encapsulate what you can do with the plugin. We unfortunately likely won't have time to go over Steppables. Steppables are relatively simple. They do look essentially the same as your Python Steppables. You just have to translate it into C++. I can, yeah, and there's plenty of links for examples of how to build a Steppable in the current documentation. As a reminder, my name is Michael Getz. I'm part of the Glacier Lab, and I guess we haven't thanked funding since this morning, so I will thank funding again. So what we're going to be talking about in this section is, first off, what do I mean by Steppable and plugin? How to create a plugin using Twedit, Twedit shortcuts and IDEs, and then we're actually going to be doing an example plugin for the Schwarz model. So Steppables and plugins evaluate at different times. That's the biggest thing that you need to know about the two when you're selecting them. Steppables are modules that the simulator will call at each MCS, like your PDE solvers. These essentially are exactly the same as the Python Steppables, but the key difference is these will be evaluated first. All of the C++ Steppables will be evaluated before any Python Steppables will be evaluated. That is something that you would need to understand, which can be advantageous, or depending on what you're trying to do, if you're trying to make Python modifications, this could become an issue. You just need to know the order of events that it's being evaluated at. For plugins, there's two large things that these plugins can do. The plugins can do a lattice monitor. So these modules are called each time the CompuCell3D function, as in MetropolisFast, makes a change to the cell lattice, meaning whenever you have a pixel flip attempt accepted, it will call this lattice monitor, right? And then the energy function is as it seems. This is the module that is called every pixel copy attempt by MetropolisFast to compute the contribution to the overall change in energy of a proposed pixel copy, right? So what is MetropolisFast? MetropolisFast is simply just the iterator that CompuCell uses to evaluate and attempt the pixel flipped attempts, right? So your probability is e to the negative h over t. This is something that you've probably seen very early on, but as a reminder, this is how you inform your pixel flip attempt probability, depending on your delta h. That's your change of energy. Right. So how do we set up a plugin? Well, it's actually pretty convenient if you do use Twedit. So I will go through on mine really quick here. I won't actually generate it, but I'll walk you through the points until it's generated. So you can open up Twedit. Then you can go to CC3D, C++, and then just generate new module. You will then get this box to open up, where you have a couple options whether it's a plugin Steppable, and then what the plugin functionality is, or where do you want it, right? So again, CC3D, C++, generate new module to get this screen up. Okay, so you can do that. You will get this box that will appear where you can specify the module name and then what kind of code layout you want. We will just be discussing main code today, right? So name of module, directory of module. This is important. We'll talk about where we target. Okay. Where we'll target this directory. We're going to keep it in main code. We haven't set up developer zone, so we're just going to generate the plugin. We need to specify whether it's a plugin or a Steppable, and then what plugin-specific options we want to perform, right? So where do we want to target? For Steppables, we will target to the Steppable folders. So it's a lot of CompuCell3Ds, but it's CompuCell3D, CompuCell3D Core, CompuCell3D Steppables, similar for plugins, right? So if I actually go to, let me pull up, I can show you here in an interactive way. Here we can do it in 4.9. So CompuCell3D, 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 Core, CompuCell3D again, and then you'll see plugins and Steppables. These are the folders you would want to target, depending if you want a Steppable or a plugin, right? Yeah, there's just one big slide deck that I put together. Sorry about that. So let's make a plugin, right? So we're going to name this plugin AdhesiveSat, and then we're going to target our plugin folder. We're going to select plugin, keep Python wrap checked, and then we're going to check energy function and lattice monitor, because we will end up needing both of these functions. I'll wait here a second if you want to follow along with creating a plugin. It will then generate a bunch of files. We'll talk about that here in a second. Just make sure that you're targeting your plugin folder. Yes, we are checking both energy function and lattice monitor, because we need, for this plugin, we need both of those functionalities. When you then continue that, you end up creating a whole bunch of files. Twedit's going to open up about 10 files that will all open up. These are our set of make list texts, and then a couple header files and CPP files. There's a couple things you can do with this. If you go to the proxy file, you can change how it's referenced in the XML, and you can provide a brief description if you want to. For this, we're not going to worry about that. We're going to keep the name and description the same. So we're going to keep AdhesiveSat and auto-generated plugin description. Okay. There's no changes we need to make there. What it's also making with all of these files are things like the CMake lists. All this is doing is basically telling the compiler that this new folder exists and it needs to access it and read its CMake file to compile the functions that you're going to end up writing into the C++ file. But the most important files to focus on for our functionality are the CPP and header files. Specifically, our AdhesiveSat plugin.h file and AdhesiveSat plugin.cpp files. Okay. these are where we're actually going to be writing in the modifications to the code. So when we look at these header and CPP files, we're going to see for the header files, it basically instantiates a couple of things that are necessary for the header file, such as the Potts simulator, the simulator itself, automaton, boundary strategy. These are basically operations that the CPM needs to perform. And then it's going to define your changeEnergy field3D change. And in the CPP file, here's a blank one that I have ready. So field change is going to basically create an empty function that says if new cell else, if old cell else. We'll talk about what this means in a second. And then your changeEnergy does the same thing. You say, well, what's the change in energy dependent on the flip of the point, right? So point is the target pixel, the pixel that is getting flipped or attempted to be flipped in, okay? We'll talk about that more specifically here in a second, but it's going to basically make these empty constructors. And what you can do is you should be able to compile it already. It's just not going to be doing anything. But it should compile okay. The most that will happen with Windows is it might, when you hit all build, it'll say, hey, I realized the solution was just updated. I need to refresh. And then you'll need to rebuild after that because it basically builds the linker to figure out, oh, this new folder exists and I need to build it into the solution. Okay. But we don't need to worry about that too much yet. What we should also think about, as a quick kind of tip, if you do kind of blank out and need some help similar to these Python, let's open this up and I can show it directly. Okay, we're just gonna look here, right? So we've gone through these CC3D Python helpful snippets, right? You also have something similar for CC3 C++, and it'll let you do these a certain set of snippet specification. Like if you want to visit all pixel neighbors, you just would hit this and then this. You need to be open in a C++ file, otherwise it'll yell at you. But if you do that, you will get a block looking like this generated, where it will just go through all of the neighbors of the cell object and then report back that pixel. Okay. So another tip, it's very useful to use an IDE when you're doing this, mostly because you can do things such as peak definitions. So what do I mean by that? If I go to here, I'm going to pick this, right? So if I click on here, I can right-click on this and then say either go to definition or just peak definition, and it'll open up a little window and then show me how this is actually defined, right? That can be pretty useful if you're unsure of how this is defined, especially when it comes to C++, where you have so many pointers that it can get hard to track what's actually going on. Last comment, when you're working on your own Steppable or plugin for your project, it is perfectly okay to hard code values at first. As in, the first thing you should not be worrying about is this XML referencing. The first thing you should be worrying about is that your Steppable actually works and that these energy modifications or or pixel watchers are actually functioning correctly and doing what we expect them to do. That is the first thing you worry about. XML, swig, or whatever types can be handled later. And unfortunately, can sometimes be a bit annoying. So as a reminder, what are we trying to do? We're trying to modify the cell pixel copy attempt probability, right? So we look at our probability draw. So this is the full definition of the probability, right? So delta H minus delta over KT. By default in CompuCell, delta is 0 and K is 1. So you end up with your negative delta H over T again. And what we want to do is modify delta H such that we have a defined energy to delta H itself. This is how all of the energy plugins function. Basically, since it's always a delta H, you can just add the delta H contribution of the plugin, and it's purely additive, right? So our contribution for the functional modification that we want ends up being this right here. We can just add this delta H adhesion, which we can define as negative E naught over the difference of our number of new adhesion spots minus our number of old adhesion spots in the form of some saturating coefficient, right? So this is what we actually want to add to this pixel flip attempt probability. So we end up having to ask, how do we do that? Well, there's a couple things that we need to kind of quickly go over in terms of vernacular, right? So when creating these plugins, the focus really should be on changeEnergy and Field3D change. So changeEnergy looks at the current target pixel locations. Well, actually just looks at the target pixel location. You can retrieve the previous, but by default, it's just looking at the target. And it matches to previously used terminology. So new cell is the source pixel type, i.e. the pixel that is trying to flip into the pixel you're looking at, right? So if a cell is moving into a space, this would be that pixel moving into that space, say, overwriting medium. That's your new cell. While old cell would be the pixel being copied over. So if you have retraction of a cell, so a cell is moving out of a space, you would have medium overwriting the cell. And that cell would then be your old cell, right? So new cell is the cell that is attempting to move into the space. Old cell is the cell that is trying to move out of that space. So with these two contributions, we can use it to calculate the delta H contribution because we can figure out how much energy is contributing by the new cell movement and the old cell movement to inform the probability percent, to inform the probability of flip, right? Well, Field3D change evaluates after a successful flip attempt to perform these operations, i.e. after this is evaluated, it says, I've passed my probability draw. Then it will access Field3D change. So then you can do some sort of modification to, say, a term or say the area of the cell, right? If I grow the cell, if the cell flips an old cell, it grows by 1, I need to then immediately recalculate the surface area, right? That's when Field3D change would come into, would be useful, right? So I'm going to try to make this kind of interaction interactive. So either feel free to try to answer. So the first thing we need to know, say we have a cell on some field. We need to know how many cell sites are occupied at initialization. So the first question we need to go through is, how would we define the initial site occupancy of a cell, right? So say we have some field that has a Boolean value of whether an adhesion molecule is present or not, and then over that a cell exists. You would need to know where that cell exists, how many pixels of that cell exist on an occupancy site. Does anyone have ideas how we could just generally do that? The worst way to do it would, yeah, so you could scan the whole lattice pixel by pixel. It's an initialization process, so it's not like it's doing it all the time. So that's not too bad. Find where medium is, and then take the difference from the whole space. So you could do it that way, where you find medium and then just take the difference, since you would technically know. But at that point, you can just go, yes, by site, they would mean lattice pixel. But I think it ends up being just about as expensive as just going through cell pixels and then seeing what that field value is, because you need to assign it to that cell, right? So it's as simple as we need to update or decrease the cell object count depending on the local pixel's adhesion spot or not. So we can just, since it's a Boolean, we can just say, hey, is the adhesion value at that point greater than this? And then we can add at that cell, we can have that cell gain an occupancy site, whatever cell is existing in the space, right? It's really that simple. You don't need to overthink it. There are some like optimizations where you only really need to check cell pixels, so you don't need to check the whole field. But you'd end up with the same outcome. One's just slightly more efficient, right? So, okay, we have a cell that knows how many adhesive sites are now occupied, right? So now we start to ask for our field 3D change. We know this evaluates after a successful flip attempt, and we need to track the number of occupied spots. How could we do this? So as a reminder, field 3D change will evaluate whenever a pixel flip is attempted. So essentially when a cell gains a voxel. Or loses a voxel. You have the right idea, Clara. I think you might be slightly overthinking, because you do know which pixel has been flipped successfully. So you know the lattice site that has been flipped. So it does end up being as simple as, okay, I'm checking the point that I know is just flipped. If I know that there's an adhesion spot there, because there could not be an adhesion site there, all I need to do is add an occupied adhesive site to new cell or subtract occupied adhesive sites from old cell, depending whether something is entering or leaving the space, right? So we know the spot. We just need to check to see, well, is this an adhesion spot? If it is an adhesion spot, if a cell is entering the space, we can just iterate it by 1. If it's leaving the space, we can do something as simple as subtract it by 1. So pretty easy so far. So now we can talk about the change energy. So this is how the energy contribution is being evaluated, right? How this specifies how this Hamiltonian is modified. So what we need is we need to know the current number of occupied spots and then figure out how the flip will modify this value, right? So how can we do this? I'm going to quickly kind of go back and try to remind you what this looks like, right? So this is our delta H that we are trying to look at. So when thinking of the definition in terms of old cell and new cell, how would we define this energy functional modification? Yeah, so that's the right idea. We need to do something similar to what we had previously just done, is we need to calculate the changes in energy depending on the loss or gain of a site, right? So we need to first check at this point we're flipping, is this an adhesion site? If it's not an adhesion site, we don't want to do anything. If it is an adhesion site, new cell will gain one. So new is its new occupancy count, old is its old occupancy count. Old cell will lose one, right? So new cell gains one, old cell loses one, and then we can just use our difference that we previously saw to see what is our delta H. We can then do the summation of these two delta H's to find what is our total delta H contribution, right? So pretty easy, still pretty direct, which is great. So our pseudocode seems to make sense. It's not doing anything crazy. We're just checking to see at these points whether it's an adhesion site, and then keeping a tracker of the number of adhesion sites. Unfortunately, pseudocode's always very clean. Then you go to actually code it, and it gets a little bit more messy, right? So when we start to think about the code, we need to define a lot of things, right? So we need it to understand that there is this adhesion field, that this adhesion field has a name, and that there is a member group attributed to this cell that tracks the number of sites that are currently occupied, right? Basically keeping a track of the number of occupancy sites that are currently modified, that are currently used. So the biggest thing here is that we then can define some function, Adhesion-energy, which you can see needs to be modified, defined in the header. That then defines our negative E naught occupied area over href occupied area, right? Here is your Michaelis-Menten term. This will make it very easy because then we can just call adhesion-energy whenever we need to do this functional. Then we also need to be able to retrieve the number of occupied cell count of the cell, which can be done by using cell extra attribute pointer, right? And it will just return this result. So all you're essentially doing here is making an extra attribute pointer associated with the cell for these occupied adhesive sites. This is a way on a cell-by-cell basis you can track how many adhesive sites are currently occupied. Right. So if I look in code itself, right? We have our adhesion energy. We have a functional to get that. We have a check to see if it's an adhesive site. And then some initializations, which we will go over later. Right? So these are the types of things that you would need to define to be able to do this, right? We need to know, we need to know our terms E0 and href and aref. We can then define it as a fixed value, or we can define it in the XML, which we will do at the end of this. Now we can start to think about, well, how do we actually start to apply these terms? And I'll go back through the code. What I'm trying to do right now is get the idea of the intent of the code before talking about a lot of the little pieces needed for the code, okay? So we can now, since we have these defined, we can start to look at our changeEnergy functional, right? This is how we apply our modifications to the actual energy function. So as we defined in the pseudocode, right, we can put a check. Is this not an adhesive site? If it's not an adhesive site, we leave. We leave this, this call. There's no point in evaluating this spot. If it's not an adhesive site, we don't need to waste any energy there, right? If it passes that check, we'll initialize the delta H. Then we will find our old count by just using this function we defined in the previous slide, get occupied cell count of the old cell. We then get the proposed, which for old cell, because it is moving out of the space, we would lose a site, right? So we make the proposed site occupancy -1. And then we add that to this delta H, right? So adhesion energy is what we just defined in the previous slide. And we're just substituting proposed occupancy and old occupancy and subtracting themselves together. So to go back very briefly, right? All it's doing there is calling adhesion energy and then substituting occupied area with the old or new, and then evaluating this functional, right? So for old cell, we can get our delta H relatively easy by just calling this function and then calling the occupied cell count and subtracting 1. Similarly for new cell, since it's moving into the space, the only real modification we need to make is that it is gaining a pixel site. And then we will do the same operation of proposed minus old. So I'll pause specifically on this slide here. Is there any questions in terms of how old cell and new cell are modifying this delta H? As a reminder, this delta H is just added directly onto the sum of all of the other delta H's. So all that really needs to be defined here is the delta H contribution of this interaction specifically. So is there any questions specifically towards the way that change energy is here? Yes, so this is exactly what would go in that block. Just bearing in mind that without defining the adhesion energy function or the get occupied cell, the get occupied site count, function, it won't succeed because these haven't been defined yet. ChangeEnergy is already declared too. So we can go back and kind of go through everything that needs to be. There's actually a lot that needs to be changed in all of these files, but specifically trying to look at very important determined modifications that need to happen for our pseudocode to be realized. For an MCS, this is called multiple times. This is called at every flip attempt. So off the top of my head, CompuCell will do the amount of flip attempts as lattice sites that exist on the field. So it's probably evaluating this energy thousands of times per MCS. So I can grab this block and put it in. So hopefully it's not too long. Here's the raw code from the working version. There's a couple extra checks that are unnecessary, but this is your changeEnergy definition. This file is also in the distributed Google Drive. Right? So is there any question, again, here in terms of how changeEnergy functions to change the energy fittingly? Otherwise, I will move on. So the other part that we need to do is we need to make sure that we're actually changing this value of occupancy site. What we're doing here is using we're using integers to say the number, but we're not actually writing back to the cell object, right? So the cell doesn't know whether or not it's actually gained a site or lost a site. To do that, we need to look into field3D change, right? So remembering our pseudocode, it ends up somewhat similar. And remembering that field3D change is evaluated at every successful flip attempt. So not every flip attempt, only flip attempts that actually succeed. We do something somewhat similar. We start by checking to see if the pixel that was flipped is an adhesive site. If it's not an adhesive site, we have no changes to make. We just leave. If it's an old cell, we need to get the data accessor and find this attribute pointer, and then subtract one site, right? So what we basically created here was a pointer called old data, which is defined as the AdhesiveSat data accessor, which retrieves old cell extra attribute pointer, and then it just subtracts one value from the occupied adhesive site for this extra attribute pointer, right? And then new cell does the same operation to basically create this pointer called new data, and then new data would gain a site. All these operations are effectively doing is modifying the actual attribute pointer on the cell object. So the equivalent in Python is if you had some custom data attribute, just changing that up or down 1. We're just getting this extra attribute that we created, and then either subtracting 1 or adding 1. This is the point where it can get a little obtuse because we're starting to look at pointers and cell object attributes, and then modifying those, but actually modifying those values as opposed to just retrieving them to do an evaluation. Does this make the cell increase, reduce the field value? No. All that this does is that this just adds 1 or subtracts 1 from some cell attribute, right? So the cell will have some attribute called occupied adhesive sites that's associated with the cell object, and all we're doing is adding 1 or subtracting 1. We are doing nothing with the actual field values. We're just creating a tracker for the cell to know how many adhesive sites it currently contains. Are there any other questions in terms of what Field3D change is trying to do? Let me grab that. I can dump this one in the chat also. Similarly, without defining some of the functions that are here, this won't work out of the box. The one that will be pasted in the chat has a couple extra lines in it. Basically, it's playing around with lock pointers to make sure that if you're multi-threading, you're not trying to modify a value twice in the same instance. So, but for the most part, if you're writing your own plugin, I would suggest you don't really worry about lock pointers. On the first time you try to write a plugin, you just assume that it's a single thread, as in there is no multi-threading. We don't have to worry about any of that mess. Everything just occurs sequentially. So you don't have to worry with pragma and p-critical or lock pointers or any of that. That's a level of complexity that can come later. We got to get it working first. Okay? So the other thing that we would need to do, and I'm just going to go through the code for these, is we need to initialize the field itself and then do XML definitions. It's actually not too bad to do XML definitions by themselves, but I would keep it all the way to the last, right? So what we need to do is when we're initializing this AdhesiveSat plugin, we need to initialize the Y field. This is called because I hard-coded a 200 by 200 lattice that forms a Y with thickness 7. It is purely hard-coded. It does not talk with a Python layer. You would have to change the this function itself to modify that. But we're just trying to create a shape in the C level that the cell can see. And the other thing is we need to initialize occupant site counts. This is what we talked about earlier with the pseudocode. We just need to go through the pixels and then see if a lattice site exists and whether there's a cell there, right? As discussed, there's probably optimizations you can do with the way it currently exists, like only going through cell pixels and then checking for the number of adhesion sites. So we need to initialize those fields. They're written in the C++ defined in the H file. And then there's another function called the update function, and that's usually where you'll put your update definitions. So at this point, I do find trying to do some of these walking through some of this code in slides rather cumbersome. So I'm going to just start kind of showing in the code some of these, right? So for instance, right, here's our extra init, right? All we need to do is call these two functions, initialize y field, initialize self counts. These are also just functions defined in the C++ file. I'm not going to go into what this is actually doing. All it's doing is just making a y. It just makes a y. That's really all you need to know about that. And then occupied cell counts will just go through all existing cells and then build this cell inventory for this extra attribute pointer, which we discussed as the number of cell site occupancies. So in this one, I wrote it just to go through all of the pixels, see if it's an adhesive site. And if it's an adhesive site and there's a cell there, all I do is I get this extra attribute pointer and then add one to it. Very simple, probably not the fastest. That's okay, it's initialization. We only have to do it once. Okay, so going back to some of the other functions that there probably is interest in. Sorry. Right. So here is how we defined the energy function itself, right? This is your adhesion energy. There's a little safety call to make sure that we don't get negative occupied area. That shouldn't ever happen, but it will at least prevent a div by zero operation if it goes really wrong. So all we're doing here is just returning this E0 occupied area, aref occupied area. Occupied area is the call for adhesion energy. For this to function correctly, we would need to define it in the header file additionally, right? Actually, I can show the deep definition, right? So you can see that it's defined in this header file. I can, right? It is this. And that will actually be able to call it in the header file. So you can see also in the header file, you have changeEnergy. These should be defined by default. You have your update. These should be defined by default. Sorry, it's this one that you actually want. I copy-pasted the wrong line. So this is how you actually define this function, right? Similar to occupied site count, adhesive site. And we can go through briefly on what those are actually doing. These are just little functions that were built in to see whether or not right? Whether or not this adhesion field is at that point. So this is just purely a call to say, all right, adhesion field at that point is a not zero. And then it will just say yes or no. Right? Get occupied cell count. Just calls the extra attribute pointer. Right? So I'll actually paste this one in. So really the hardest thing that needs to occur here, I'll say in my opinion, is just making sure that this extra attribute pointer is created correctly, right? So at this point, is there anything that anyone's finding confusing in terms of this, in terms of some of these earlier changes, right? changeEnergy, field 3D change, or how this Adhesion-energy function is called or initialized. Feel free to ask in chat, and I will do my best to answer it. Very briefly, you can also define our XML attributes like this. And so I'll copy this whole thing. As I was talking about in the update, all you are doing here is basically reading the XML element tree, then looking at this element that's we end up defining. We're looking for E0 and aref, and then just saying, well, if this exists, I need to get that double, get that value, and assign it to aref. Right? Then we have a little error message here that says, hey, aref needs to be positive. You can't have negative or zero reference binding sites. Right? So let me quickly show you. Oh, I already do have it open. Okay, let me quickly show you in Twedit what this would look like. I briefly showed it earlier. So this AdhesioSat XML, we would, like all the other plugins, make this plugin block name that associates to what was set in the proxy. We didn't rename it, so it's just AdhesiveSat, and then we can say what values we want of E0 and aref. And it will pull these values and then pass it down to this aref and E0 value. The order in which we paste this within the C++ is also crucial. No, not really. As long as you're not accidentally embedding these calls within each other, it shouldn't care about the ordering. So, yeah. So I will go from the top and start to explain of everything that's happening in this. The header file really is just declaring everything. That's all you mostly need to know about the header file. It's a declaring thing, and then it will initialize some values at 0. Right? You can see it's declaring these values. It's declaring all the functions. And then it's declaring the extra members group accessor. Right? So I will go from the top down with what is actually in the final version of the plugin. A lot of this is automatically generated, so you don't need to, it's already there, right? But what's happening here is it's saying I need to have this CompuCell header file, so it's got all those declaration. I need to have the AdhesiveSat plugin header file, and I need to have the CMath and algorithm libraries. I'm going to use the CompuCell3D namespace. And then I'm going to initialize a set of values, right? So most of these null pointers you don't have to do. But you do need to define adhesion field names as adhesion sites, enot, aref. These are just some non-zero values, so it can. Yes, I would not define everything in the C++ file, the CPP file. It does get very messy, and you can't just create header linkers. I really would keep them separate. So the big things that are defined here in the AdhesiveSat plugin are just what's the field name, and then some initial values for enot and aref in case it's not defined, but you're still calling the value. We want to make sure that it's giving some value. So these are just safety values that I put in. They're not very important as long as you're actually defining the XML, right? Right. This is just lock pointers. This is basically to make sure that it's not trying to access the same site at the same time when it's multi-threading. I wouldn't worry about it. Multi-threading is a pain. I don't think I fully understand it half the time. So we then can start to move into our init function. This should be constructed the same by default, right? So we need to know sim, pots, cell field, field dim, and I have this error assertion. This is purely because this is so hard-coded. I need to make sure I am forcing the simulation to use a 200 by 200 by 1. This is because I have to initialize a field in the CPP file. So I need to force to make sure that it's not being defined differently elsewhere. This is purely because I had to define in the CPP file, and we can talk about that briefly and try to brainstorm ways around it. So then we make our data accessor, right? So we register this class. We create the generic scalar field. This is your adhesion field. We assign the field name that we went over earlier. And then an error in case it fails to create this adhesion field. All right. Don't worry about the lock pointers again. Then you do update XML data true. This is basically trying to read the XML and then updating those XML values. Right. So in this, it would be your enot and a values, aref values. Right. Then we register this energy function, AdhesiveSat. And I mean, these are standard ones that it should automatically create. Right? It's basically creating these pointers to this cell G object, which is your cell object, and steerable object, which should be something like the steering panel. Right? Our extra init, where we make our Y field, we'll go through that briefly in a second, and then count the number of occupied sites. Right? So if we initialize this Y field, again, I'm not going to go into exactly what it's doing. Basically, it's going through the field and creating a Y, depending on the value at the grid space. Right? That's all it's doing. It makes a Y. I think I already pasted that one in. If I didn't, I will just repaste it. It's fine. So this is to make sure that you have a field that can be referenced. Now, you might be wondering, why is it here? Why are you initializing this in the plugin? Well, the biggest thing is, I need this field to exist before it evaluates it initially. Right? I need to make sure that this field exists. So the easiest way and quickest way that I could do it is by just writing it into the initialization function for the plugin. Now, there's some good brainstorming that can be done here of where could this, in theory, be placed, right? Remembering these kind of order of evaluations, and that your plugins will be evaluated, then it should be your C++ Steppables, and then finally your Python Steppables. So if you're trying to define this in the Python Steppable level, it's going to be hard to then retrieve this back in the Y field, or in the plugin. So does anybody have ideas on how you could try to initialize this field and then have it read in and be properly initialized for the initial count, right? But the reason I'm asking is because these are kind of the things that you do need to slow down and think about a little bit in terms of in what order are things being accessed? And if I say I'm initializing this cell count or this cell occupancy dependent on a field, am I sure that field exists by the time that I do this initialization, right? Because if you do it out of order, it will just go through this evaluation, and it won't really care that it initialized the 0 values and then made it the field. It's already assigned this values. It's passed the computer's passed that. It's probably not going to tell you anything unless you get a div by 0 operation, right? So the easiest way that you could do it is put it in there. The other is you could try to utilize start functions and then make sure that this is being the number of adhesion sites is being counted correctly by simply doing something like this, which is, I think I kept it in there. So this is how I was checking to make sure is that you can do a cout argument by saying, when I initialize, how many occupancy sites do I have? And really, you're just looking for something greater than 0 if you know that the cell is being initialized on a site, right? So I should probably just collapse these, huh? Yep. So for instance, if I look at my get initialized occupancy, you can basically, at the end of this initialization, you can have it cout the number of occupied adhesive sites, and you're just looking for values greater than 0. Then you know that it did initialize after the field, which is what you want to see. Because otherwise, the way that field 3D change is written and the way that energy, the change in energy is written, it's just going to be going up 1 and down 1 off this 0 value, since it's only making integer modifications, and it will just forever be that wrong number due to the wrong order of initialization, right? So altogether, we should end up with an initialization where we can see the adhesive site forming a Y. For this, with the provided file, we are just making uniform initializer with a cell that's in the center with some width of type A. There's only type A in this field. So we can see that in the center. And then we can let it run with whatever provided values, noting that we have no volume energy. We only have surface energy and contact energy. The contact energy makes sure the cell stays together because it's going to like itself. And then the surface energy is just to create some sort of impedance towards spreading growth, right? So we can then run that, and we see this type of spreading behavior where it will try to follow the Y while filling out the spaces between that, because it doesn't really see energy penalties here. It just doesn't see the favorability of these red zones, right? So I think, unfortunately, we are getting towards the end. This is a lot. I know it's a lot. I really encourage questions. I have provided the whole plugin, the whole working plugin. So you can go back and read it, or if you are reading it, anything that you see that's confusing, anything I've discussed right now that you find confusing, right? Once you define that plugin, can you automatically call it in Python via I can't say much about that. A lot of these changes, or to get it accessible truly into Python, sometimes you're dealing with swig modifications. If you are using the Python, no, because I don't think it makes, the only thing it reads right now is an XML. So it's not actually even checking to see if there's if it's Python or telling it to try to read Python. So I think, and you can try it yourself, Pedro, I think it will fail if you try to assign it with the Python only interface because it hasn't been told how to read that. I don't think the Python only interface will make an XML intermediate. So both this file and the other file are provided. Fully encourage you to just open it up and play around with these values. If you turn lambda volume off, it does a lot more interesting things. If you go back to the original paper that we stole the fourth term only off of, they do talk about why they don't have an area constraint, or in 2 dimensions, right? Our volume constraint is an area constraint. You mentioned there are issues that the field is defined in the wrong order. Okay. Let me try to do, you'll have to forgive me. This is the easiest paint thing I can find. And I am drawing with a mouse, right? So please stop me if it is so badly drawn that it does not make sense, right? So for our simulation, we have this y, right? And then on this y, the cell will be initialized, right? So we'll just say that, right? And what we're concerned with is in this initial state, how many of these pixels in the y overlap with that cell area, right? So in the correct order, we just go through these cell pixels, and then we count if an adhesion site exists. But if we define this y at the Python level in Steppable, even worse off, I'll guarantee you that'll be not defined in order. Then what's actually initialized when you are counting that cell, when you're going through the cell pixels, is what it sees is just itself in an empty field. It will see 0 values everywhere for these for the adhesion values. And then afterwards, this y will be built, but nothing happens to the cell to tell it that it now has occupancy sites, right? So this cell still thinks I have no occupancy sites, even though it should have occupancy sites purely because this y was built after the cell initialized its number of occupancy sites. So then as you move forward, the cell will always have a value that's offset by the initial value, purely because the way we wrote it says I either add 1 or subtract 1, and you will be adding 1 or subtracting 1 from this wrong initialization. So you're going to basically always have an offset of this bad initialization. In short, you're going to have basically a delta A, right, of just your value will always be minus AI from the actual initial value. So as opposed to just being AF, you're always going to have this minus term on it. Yes, exactly. It gets disconnected with the field without a way to become reconnection because it was initialized improperly. And these are the kind of small things that you need to be on the lookout for really generally when you're building these, when you're building a model, even at the Python level, making sure your order of events is correct and you're not creating, basically instantiating some value after you've already tried to instantiate something that's related to that value, right? So I would encourage you to go through the code, go through the example, take your time. If you want, feed it to ChatGPT, feed it to Claude, get it to kind of break it down and talk to you. There is unfortunately a lot more than I initially wanted for this example, but I really wanted to focus on the things that you need to be thinking about when you are building these types of plugins, when you would need these types of objects, and then how to make those objects. And everything else past that is just getting the simulation to actually work through initialization, through pointers, through all that. And really, Claude or ChatGPT can help you a lot in making sure these pointers are created successfully. If you don't know how to create them already, But do make sure that they are creating them correctly. They're not perfect. Don't offload all the thinking to your LLM of choice. Is there any other questions? Otherwise, I will go through some final comments. Erythra, there's also a zip file that contains a complete plugin. So there should be two plugins. One will be the CC3D simulation file, and one will be the plugin that I'm showing you here. It's just a zipped version of this plugin, which does work. So all you would have to do is, with your ill-defined plugin that you already have, you can just substitute the .h files and the CPP files with the files that are in the zip file, and then compile it. And it should run OK. If you do hit any issues, feel free to ask me or email me, depending on when you hit the issue. And I can help you sort it out. And that offer is open to everyone. If you do hit issues or you do get confused kind of parsing through this, feel free to ask. And I will answer. OK? But it should run. This is what I have running on mine. I've shared both. Just make sure you've compiled it and that you've substituted the H file and the CVP file with the shared plugin. Everything else is the same. The CMake files, the CLists, they'll all have the same pointers. The only thing you can directly substitute the .h and the .cpp files. Okay, so some final comments. The plugin that I've shared with you and kind of walked you through mostly through the pseudo idea today is the pseudocode idea with some limited code today is not ready for a CC3D release. There's a lot of hard-coded things. But if you do want to contribute your plugin to release for CC3D, you are welcome to. But it will need to be extensible, meaning that there needs to be some form of error checking that's rather robust. You need to make sure this method works in both square and hex lattice types across all copy ranges and in 2D or 3D environments. Or if it only exists in certain types, you need to make sure it throws an error when it reads the XML or Python definitions and then says, I can only do these types of these types of models, right? So you should have a CC3D ML counterpart, be Python controllable, and then you would want to include documentation with clear explanation of purpose and function at the mathematical level. And then we would want to see method demos. So James brought up a point. So 2D modules are allowed, but you do need to throw an error if you do try to load this module in a 3D, which is the exert or throw argument. Yeah, square lattice the same. If you do want it to be limited, you just need to make sure that it will throw errors if it's trying to be loaded into the wrong type of simulation. Is there any good reference document for determining if a plugin is sufficiently extensible for contributing to CompuCell3D? That's a good question. For the most part, it would basically be for testing extensibility. You would basically want to contribute it to the CompuCell code, and then just a whole bunch of people test it and we see if it breaks. As I understand it, that is the current workflow. I do not think in the developer's manual there is any comments on what we mean by extensible.
I was going to say, if somebody actually wanted to write a page explaining what we expect for documentation and capabilities for extensions, that would be really useful to have on the CompuCell page. That was a great question, Kyle. Somebody wanted to take a stab at that. I'm sure there's some standard boilerplates we could use for other open source packages that could be modified for that purpose.